Welcome to Herdley. Each book is distilled into 3 stories, giving you the key ideas in minutes. Today we study together Johnson and Lenhard's book, Cultures of Prediction, How Engineering and Science Evolve with Mathematical Tools, in which we probe into the co-evolution of mathematical models, prediction practices, and computational tools as drivers of scientific and engineering progress over centuries. Ann Johnson, 1965-2016, was Associate Professor of Science and Technology Studies at Cornell University. Johannes Lenhard holds the Heisenberg Professorship in Philosophy in Science and Engineering at Rhineland-Palatinate Technical University, Kaiserslautern-Landau. Don't go away, Herdley the editor. In today's stories, we'll follow a mathematician grappling with the chaos of cannonball trajectories, a visionary engineer navigating the uncertainties of complex systems, and a chemist who redefined prediction in the age of computers. The first story takes us to the 16th century, where the Italian mathematician Niccolò Tartaglia stood on the front lines of early ballistic science. He was tasked with solving a problem of paramount importance in warfare, accurately predicting the trajectory of a cannonball. Tartaglia, like many of his contemporaries, relied on simple geometric models and empirical data, but the accuracy was often far from what was needed. His breakthrough came in the form of a tool he called the squadra, which allowed bombardiers to measure angles of elevation and thus improve their aim. However, as Tartaglia soon realized, the chaos of the real world, the irregularity of cannonballs, the unpredictable winds, and the uneven ground, rendered his models inadequate for fully reliable predictions. Still, Tartaglia's work set the stage for future developments in prediction by introducing the idea that mathematical models, even imperfect ones, could be valuable tools for practical purposes. His balancing act between theory and practice is captured in a telling passage from the book. Tartaglia permits a baffling inconsistency. He first questions the straight lines, then uses mathematics to analyze the trajectory of a projectile. While Tartaglia's model wasn't perfect, his contribution was crucial. He opened the door to future improvements in predictive tools by making it clear that even flawed models could still have immense practical value. The lesson here is that even when predictive models are imperfect, they can still serve as useful tools for guiding actions, provided their limitations are understood and managed. To improve predictions, one must continuously refine the models based on real-world feedback, just as Tartaglia's successors did. From the struggles of Tartaglia, we fast forward to the 20th century and meet J. Forrester, an engineer at MIT who faced a new kind of chaos, the unpredictability of complex systems. Forrester was tasked with creating a model that could predict the behavior of intricate systems, from corporate structures to the global economy. His work on the Whirlwind computer system, initially developed for military purposes, evolved into something far more groundbreaking: the creation of systems dynamics, a method for modeling and understanding complex feedback loops in large systems. Forrester's genius lay in his ability to recognize patterns in chaos, using computational tools to simulate systems that would have been impossible to analyze with mere human intuition. His model reached a pivotal moment when it was used to predict the future of global resource consumption in the Limits to Growth study. This study, though controversial, made a lasting impact by showing how interconnected variables such as population, industrial output, and resource depletion could lead to catastrophic outcomes if not managed properly. A quote from the book encapsulates this: "Thinking about the future and political decision-making moved under the umbrella of a culture of prediction." Forrester's work pushed the boundaries of predictive modeling and showed the world that even the most chaotic systems could be tamed through the right combination of mathematical tools and computational power. The lesson from Forrester's story is clear. Understanding complex systems requires embracing their feedback loops and using computational tools to simulate possible outcomes. It's not about getting every prediction right. It's about understanding how the components of a system interact and where those interactions could lead. As Forrester's predictions about global resources stirred public debate, another figure, working quietly in the background of science, was transforming prediction in an entirely different way. In the 1990s, the field of quantum chemistry was revolutionized by a shift in how chemists used mathematical models to predict molecular behavior. At the forefront of this change was a group of computational chemists who embraced a new culture of prediction that relied heavily on iterative processes. Density functional theory, DFT, became the tool of choice, enabling scientists to predict the properties of molecules with unprecedented accuracy. Unlike traditional theories, which sought to explain phenomena first and predict later, DFT was primarily concerned with prediction. The shift from theory-driven to data-driven modeling was profound, as chemists now relied on massive computational power to iterate through thousands of possible molecular structures in search of the best fit. This change is described in the book as an exploratory iterative culture of prediction that leads to a further orientation toward predictive success at the cost of explanatory potential. In other words, chemists began to value predictive accuracy over deep theoretical understanding, a dramatic shift from the traditions of science. This story shows us that, in some fields, prediction can become an end in itself, where the focus is less on why something happens and more on making sure we can forecast what will happen. What we learn from the quantum chemists is that the future of prediction may lie in iterating through vast amounts of data and honing our models until they fit reality as closely as possible. The key is to accept that in some cases, the best path forward is through trial and error rather than seeking a perfect theoretical explanation. These three stories, Tartaglia's early attempts at predicting cannonball trajectories, Forrester's pioneering work in systems dynamics, and the chemist's shift toward iterative prediction in quantum modeling, highlight the evolution of prediction practices. In each case, the models improved not by seeking perfection, but by incorporating real-world feedback, computational tools, and iterative processes. Prediction, as these stories reveal, is not about knowing the future with certainty. It is about navigating uncertainty with the best tools available at the time. As the editor of Hardly, by learning from these stories, we can see that the future of prediction will likely rely even more on iterative, computational approaches. These methods may not always give us deeper understanding, but they will help us navigate complex systems and make informed decisions in an increasingly unpredictable world. Each story comes from the most representative. As we come to the conclusion of our exploration, the overarching theme of cultures of prediction becomes clear: the fusion of mathematics, engineering, and science into a complex, ever-evolving system of making predictions. One of the key takeaways is how different predictive modes, rational, empirical, iterative numerical, and exploratory iterative, intertwine, shaping the outcomes of both scientific inquiry and technological advancement. A particularly striking example is the story of J. Forrester and the development of the whirlwind computer. Forrester's work in system dynamics during the 1950s became a landmark in computational predictions. The whirlwind was not just a cutting-edge machine at the time. It redefined the limits of what engineers and scientists could foresee in terms of future systems and behaviors. Designed initially for military use in the SAGE air defense system, the whirlwind proved to be instrumental in systems thinking, where engineers could model large-scale processes, such as urban growth or environmental impacts, with increasing accuracy. This was no simple feat. The computer's complexity required engineers to iterate constantly on their models, adjusting variables and testing scenarios to refine their predictions. It wasn't just a tool for static analysis. It actively changed how predictions were made and validated. The lessons from Forrester's work laid the groundwork for the computational models that followed, marking a crucial point in the evolution of predictive culture. Reflecting on these stories, it's evident that predictions in engineering and science are not just about accuracy or data, but about shaping the very methods and models we use to understand and influence the world around us. This realization reinforces the book's central idea. Predictions shape not only outcomes, but also the processes and tools that engineers and scientists